So, the goal I have for today is to talk about a bunch of identities that trig functions satisfy. And remember, an identity is like the Pythagorean identity. It's an equation that holds true no matter what input you plug into a function. So in this case, these are like facts about trig functions that are independent of input. If you plug a negative into either cosine or sine, the output value will change in a predictable way. And I don't know, that looks like it has to do with evenness and oddness. So let's just see if people just remember off the top of their head. Cosine, even or odd? On either. Cosine? I hear an even, I hear an odd. Cool, so we won't fill it in yet. If you just remember, go ahead and fill it in. Right? If you know whether it's even or odd, you know what you should do with that negative sign. When you add pi to an angle in radians, it behaves in a predictable way. When you subtract an angle from pi, same. And same with pi over 2's. And establishing each of those facts will be our goal today. So, let's go ahead and start. And maybe as a reminder, we talked through what happens when you add 2 pi k to an angle. That 2 pi k just corresponds to a full revolution. Full revolutions don't change sine or cosine. Sine and cosine don't care about plus 2 pi k. And maybe let's use that to do a quick application. Without using your calculator, using only your unit circle, let's compute the tangent of 9 pi over 4 using this idea. So I think here's the way to think about it. 9 pi over 4, is that more than 2 pi? Less than 2 pi? How big is 2 pi if you put a 4 in the denominator? 8 pi over 4. So 9 pi over 4 is a little bit bigger. So instead of thinking about the tangent of 9 pi over 4, you can think about the tangent of 2 pi plus an extra pi over 4. Cool. Does tangent care about that plus 2 pi? Nope. None of the trig functions care about full revolutions. So that's the same thing as just the tangent of pi over 4. And take a look at your unit circle, or your unit circle that you keep in your brain. What's the tangent of pi over 4? I hear some ones. Yeah, nice. And we're going to do more stuff with the unit circle, like fill in the rest of it. Pi over 4, tangent is 1. Nice. Let's carry on. Minus theta. So let's try to figure out what happens when you take an angle and replace that angle by negative theta. And maybe it's right to start by drawing a picture. So if theta is just some angle, then rotating by that angle theta means rotating counterclockwise, let's say that far. So there's this angle theta. There's a point cosine theta, sine theta. What does it mean to rotate by negative theta?
Go clockwise.
Yeah, you just rotate the same amount the opposite direction. Cosine of negative theta, sine of negative theta. Cool. So, take a look at that diagram. What symmetry relates the blue and the orange line? Now that you see them drawn. Or just how do the x and y values change? How do the x values of those 2 points compare? Yeah, the x values stay the same. The y values are additive inverses to each other. Oh, cool. And if you like, that corresponds to a flexion over the x-axis. x values stay the same, y values get negated. As in an extra negative sign appears in front of them. So that means cosine of negative theta, that's the cosine, same as cosine of 2 pi minus theta. You can add an extra 2 pi, it doesn't change it. Cosine. That's the orange x value. The orange x value is the exact same as the blue x value. So, cosine of negative theta is the exact same as the cosine of theta. And now let's go back to this one, even or odd. What do you call a function if it doesn't care if the input is negative? Even or odd? X squared, does it care if you put a negative in there? They're called even functions because they're like even power functions. So this just says the cosine of theta is even. How about sine of theta? Could you fill in the same sort of line down here? Sine is the y value. This new y value is exactly negative the old y value. Oh, so that's negative sine theta. Neato. So we have these identities. I'm going to flip back to the previous page and just put these into the table. So replacing an angle theta by negative theta, or 2 pi minus theta, corresponds to a reflection over the x-axis. Cosine theta stays the same. Sine theta becomes negative. Cool. That feel pretty good? Nice. Now let's use that to do something. So, I'll see if people are comfortable doing this on their own. Otherwise, we can talk through it. So take a look at your unit circle and use these identities. Compute for me the sign of negative pi over 3. Do people want me to say what? Cool. Then I will wait for it. Someone will tell me what the sign of negative pi over 3 is. Guess if you don't carry your unit circle on you, I think I can fit everything on the same page by zooming out. Cool. What is it? I hear a negative root 3 over 2. Yeah, right? Cool. Right, whatever this number will be, it will be the same as negative sine pi over 3. Pi over 3 is an angle I see there. There's the y value. Negative, from this negative, root 3 over 2. That also tells me what I can put down here now. The sign of negative pi over 3 is negative root 3 over 2. In fact, what do you think? Could you fill in all of the sine and cosine values in quadrant 2 now? Nice, do it. Unless you already have them. Guess it was in the notes, so people may have just done it in advance. Let's go through it. So, starting at pi over 6, what should cosine of pi over 6 be?
Square root of 3 over 2.
Nice.
Negative 1/2.
Cool. And now we'll just carry on. X value is the same. Root 2 over 2, negative root 2 over 2, 1/2. And we have enough information already to figure out tangent, right? Just do y value divided by x value. But I think we can save ourselves some effort by doing it in the abstract and then coming back to it. All right. And to figure out what I mean by do these computations in the abstract, let's use these ideas to compute the secant of 11 pi over 6. Let's try to reason through it. So I know what to do with sine and cosine, right? So if I could write secant in terms of sine and cosine, I could use that. What is secant in terms of sine and cosine?
1 over cosine.
It's the reciprocal of cosine. Nice. That's 1 over cosine of (11 pi over 6). That's certainly not an angle you see on the unit circle. But using the sorts of operations that we just discussed, is it related to an angle in the unit circle? Yeah, so 11 pi over 6 is almost all the way around the circle, right? 12 pi over 6 would be 2 pi. So I think I can write this angle as this angle as 2 pi minus a little bit. So 2 pi is 12 pi over 6. I already have to go back to get to 11 pi over 6. 1 more pi over 6. So, oh nice. As we've discussed, you don't care about the plus 2 pi, so you can ignore that. What does cosine do when you see a negative inside of the cosine? Cosine is even or odd? Even. So I don't care about that negative. That's the same as 1 over cosine of pi over 6. Ooh, now I can consult the unit circle. Pi over 6, cosine is root 3 over 2. That's 1 over root 3 over 2. So gosh, you can move the 2 to the numerator and now multiply and divide by root 3. Nice. That feel pretty okay? And I think I want to have you all now fill in one of these tables. Maybe I'll see how people feel. Do you think you could do that same operation? No, let's use secant. If you plug in a negative for any secant value, do you think you could follow these same instructions? So let's try to do that. I think I'll talk through secant, I'll let you do cosecant, then we'll talk through tangent together. So if you want to compute the secant of minus theta, let's try to figure out how to do it. Secant is 1 over cosine. So, cool. What can I do with the negative inside of a cosine? What's the cosine of negative theta? Just cosine theta? Oh, cool. So this is just 1 over cosine theta. In some sense, work on. There's like just a theta inside of the parentheses now. But which single trig function is 1 over the cosine? Secant. Oh, so secant of negative theta is secant of theta. So secant is even. Could you do cosecant now? Do some more. Figure out what the cosecant of negative theta is. And once you have some progress, or you feel like you're getting stuck at all, talk with those around you, or raise your hand, I'll come around. I'll even come around just to check answers. If people have answers, they just don't check. Let's hear it. What you get? Do people feel stuck on the computation, like they want to see me go through one more example or something like this? Okay, cool. Let's do it. So, let's try to compute cosecant of minus theta. So the first thing I want to think about is cosecant. What is cosecant? 1 over sine. All right. So now I see sine of negative theta. That's something that I know something about. What can I do with a negative inside of a sine? Yep, because this rule says sine of negative theta is the same as negative sine theta. All right. So now what do I see? I see a negative in the denominator. What does making the denominator negative do to a fraction? Like if I asked you to simplify 1 over negative 2. Pull separate. 1 over negative 2 is the same as negative 1/2. So I pull that negative out front. In fact, let's do that in a single step right now. So I see negative 1 over sine. And which trig function gives you 1 over sine? Cosecant? So this is the same as negative, from that negative sign, cosecant theta. All right. And let's do one last one. I think I want tangent because tangent's like the other thing we actually see in the unit circle. So let's just talk through what happens with tangent real quick. So carrying on down. Tangent of negative theta. Tangent is sine over cosine, so it's sine of negative theta divided by cosine of negative theta. And now let's just think about what I can do with each of those thetas. Negative inside of the sine. Is sine even or odd? Odd. Cool, so I can pull out that negative. Cosine, even or odd? Even. So I don't care about that negative. So that is negative sine theta divided by cosine theta. Oh, so what is that now just in terms of a single trig function? Pull the negative out front, and then you're left with sine over cosine, also known as tangent. Cool. So tangent, also odd, and in fact, you already knew that. Does that look odd? Yeah, pin down the origin. All right. So, what else can we do? We can now fill these in. Tangent of negative pi over 6 will be negative tangent pi over 6, so negative root 3 over 3, negative 1, negative root 3. Groovy. That go pretty okay? All right. So there's one more of those operations that I wanted. Let's think about this next one. We're placing an angle of theta by pi plus theta. And so I'll use a similar reasoning. In blue, there's some angle theta. It lands at some xy value, x equals cosine, y equals sine. Let's try to also draw an angle of pi plus theta. To figure out what that is, let's just think about what that angle of pi is. How big an angle is pi? How much of a full revolution is pi? So, if I want an angle of pi plus theta, I can go forward by half of a revolution, and then forward by an extra theta. So there's an angle of pi plus theta. All right. Orange line and blue line, what symmetry relates them? Or just how do the xy values compare?
So you have negative x and y values.
X values become negative and so do the y values. So, that's called reflection over the origin. Alright, this line and that line both come out from the origin, just in opposite directions. Both x and y become negative. So cosine of pi plus theta is the new x value, is the same as negative the old x value. That's negative cosine theta. Sine of pi plus theta is the same as negative sine theta. So whenever you add pi to an angle, you replace that angle by the same angle but reflected over the origin. That makes sine and cosine negative. That seems sensible enough? Let's use this to do something. Grab your unit circle. Compute for me the sine of 4 pi over 3. In fact, you know what? Let's do this one together and then I'll have you do tangent. Alright, so let's see. 4 pi over 3. That's a little bit bigger than pi. So I could rewrite that as sine of pi plus. Alright, so 4 pi over 3. That's 3 pi over 3. That counts for pi plus how much more? Four thirds is 3 thirds plus how much more? 1 third. So I just stick pi up there. Alright, pi plus pi over 3. Alright, so now that I've literally expressed that angle so that there's a pi in there, I can deal with that pi. By the formula we just established, what happens to sine when you stick a pi plus in the parentheses? I can drop the pi plus at the cost of sticking a negative sign in there. So, sine of pi plus pi over 3 is the same as negative sine of pi over 3. Alright, and looking at the unit circle, what's the sine of pi over 3? Pi over 3, root 3 over 2. You know what? Keep that negative sign in orange. Why not? So the sine of pi plus pi over 3, sine of 4 pi over 3, is negative root 3 over 2. That feel pretty good? Cool. Now's the one that I'm going to have you do. Do you think you could use similar ideas to think about the tangent of 7 pi over 6? I want you to do it, so I will give you either the opportunity to do it, or do you feel like you don't know how to begin and would like me to say something else? Alright, cool. Walk it out. Compute the tangent of 7 pi over 6. If you want to walk with those around you, go for it. limits are. Go ahead and compare with those around you. Once you feel reasonably confident. And I said not to use a calculator, but you can definitely use a calculator to check your answers, right? Okay, good. You are being very quiet, which always makes me very nervous. But people are bringing out their calculators, which means at least they're getting to a resolution on the computation. Good. So, Nito, let's hear what we're getting. Someone who feels confident. Yeah.
Negative square root of 3 over 3.
I hear a negative root 3 over 3. Do I hear agreement or disagreement?
I got square root of 3.
A positive root 3 over 3. Cool. Let's check. And you know what? I'm going to go with checking by resorting to machine. So, someone who's taken out their calculator and asked it to directly compute tangent of whatever number that was. Is the end result positive or negative? And then we'll go through the walk either way. I hear a positive. So that suggests that the positive option is the one we want. So let's go through and actually walk through it. So I suspect that a lot of right ideas happened either way. Let's just see where this sign error happened. So I want to compute the tangent of 7 pi over 6, but I don't have any nice facts about a weird number inside of a tangent. I only have that for sine and cosine. But tangent is sine over cosine. That is sine of, let's see, let's also manipulate that angle. So 7 pi over 6 is like a little bit bigger than pi, right? Because 7 is bigger than 6. So I can write this angle as pi plus a little bit. And what's the little bit that needs to be added to pi to get that angle? Pi over 6. Nice. Now, let's play the same game as the previous example. That pi plus. Let's deal with the numerator and denominator separately. What happens to sine when you stick a pi plus inside of the parentheses? It stays the same or becomes negative? Sine becomes negative. So I'll see a negative sine pi over 6. How about cosine? Same question. When you see a pi plus, what happens? Nope. Cosine of pi plus an angle becomes negative. That was replacing an angle by negative that angle. Yeah. So, when you do pi plus, sine and cosine both become negative. All right, and now negatives cancel. Yeah, that looks like tangent of just pi over 6. Consult the unit circle. Pi over 6, root 3 over 3. Groovy. People follow roughly that procedure? Yeah. So, I'm going to flip back to the previous page. Put things here. So pi plus an angle corresponds to a reflection over the origin. Cosine becomes negative. Sine becomes negative. And that's all that goes in this table. And the reason that that's all I'm putting in that table is because we could walk out any of the other trig functions. And you know what I figure? I figure we just did something with tangent. So let's deal with tangent first. So let's take this exact same ideas in the computation that we just did and see what happens with tangent. So I want the tangent of pi plus theta. That's the same as the sine of pi plus theta divided by the cosine of pi plus theta. And same question as we just answered. What can I do with those pi pluses? I can delete them, but at what cost? The thing on top becomes negative? Yeah, negative signs. Okay. All right, so this is why I like to say sine with a G when I mean like a minus sign, as opposed to sine the function. So negatives appear for both sine and cosine. Oh, cool. Do those negatives undo each other? Yeah. Numerator and denominator are both negative. Those negatives cancel. And what trig function is that? Tangent. Cool. So there's a cool fact here. So remember the word period. The period is like the smallest number you can add to the input of a function that resolves the function. 2 pi isn't the period of tangent. Pi is the period of tangent. Tangent is pi periodic. Cool. Do people think they could fill in the remaining entries in that table independently and on their own? Anyone want to see one talked through together? Cool. So maybe I'll encourage you to do one thing as you go through and fill in that table on your own time. Oh, I don't know. It looks like people are actually just doing that right now. Give me the end result for one of those. Well, I guess here we have 2. Give me one of the remaining entries in that table. Like that?
Yeah.
Do I hear a second? Cool. We can check. Here's how I will propose checking. I had this other Desmos interactive that I wanted to mess around with, and maybe we'll use that on the next one. So let's see. This is cotangent of pi plus, right, Desmos expects x to be the input, not theta. Nope, I typo. Does cotangent of pi plus x look the same as cotangent of x? Nice. So yeah, I agree. So as you go through and fill in that table, pull up some graphs, double check. Let's do this next one, and it's going to feel very similar. We're going to perform a very similar analysis again. Pi minus theta. So, same first step. Start by drawing an angle of theta. Now let's think about pi minus theta. And it'll be very much the same reasoning. How do you get, so how big an angle is pi? Half of a revolution. So to get pi minus theta, I'll start by rotating forward half of a revolution, and then I need to go backwards by theta. So, drawing that here. Go forward by 1 full revolution, and then backwards by theta. There's an angle of pi minus theta. And you know what question I'm going to ask next? What symmetry relates those two lines, the blue line and the orange line? What symmetry? They are reflections over the y-axis. That is exactly how you spell reflect. I'm not going to fix it. All right, it's reflection over the y-axis. What happens to x values when you reflect over the y-axis? X values stay the same, or x values become negative? And I know I said become negative, but that's not quite right. If they were already negative, they would become positive. They get negated. A negative sign appears. Y values, though, stay the same. All right. So you know what's going in the next line. Cosine is the x value. X value becomes negative. Sine is the y value. Y values stay the same. So cosine of pi minus theta is the same as negative cosine theta. Sine of pi minus theta is the same as the sine of theta. And now I'm going to go back to that cover page, that big table, and fill in an entry. Pi minus theta corresponds to a reflection over the y-axis. Cosine of pi minus theta is the x value that becomes negative. Y value stays the same. All right. Groovy. And you know what? Just because I made this Desmos interactive, I'm going to use the damn thing. So, here's a picture of, let's ignore B for now, a single angle A, and then I'll even let it change. It's going to wander around. This new angle will be pi minus A, and I'll also have Desmos graph the little line pointing in that direction too. So I'll let that A vary. Do those two lines seem like they're always just reflected over the y-axis from each other? Cool. And that's like, okay, same questions again. 2 pi over 30, let's try to compute that. So, let's start by thinking about what 2 pi over 3 is. So if I have successfully signposted this correctly, I think I want to write this as pi minus something, because that's just like the identity we have right above. Is this pi minus a little bit? Let's use that. This is the sign of pi minus a little bit. That I will highlight in orange because I want to get rid of it soon. 2 pi over 3. So 2 pi over 3 is a full pi, but then take away how much? Pi over 3. And right, like we could be doing that algebraically, but I don't think you need to even think algebraically to get that at this point. No, I want this to be green. All right, so let's carry on. Nice, so I see a pi minus in the parentheses. What does pi minus do to an angle? Nope, what does pi minus do to sine? Sine of pi minus an angle is equal to just sine of that angle? So in sine, if you see a pi minus an angle inside of a sine, you can ignore the pi minus. So this is just the same as just sine of pi over 3. And grab your unit circle. What's the sine of pi over 3? Pi over 3. Oh, I think we've referenced that same entry a bunch of times today. Root 3 over 2. That also lets me add something to the unit circle. 2 pi over 3. The sine is root 3 over 2. And notice, those two angles, just visibly, do those look like they're reflected over the y-axis? Yeah, cool. So let's now make an automatic computation. What goes in that x value? Negative 1/2. It should be the same as the x value on the other side, but negative. And I'll go through and do the same. X value becomes negative. Y value stays the same. X value stays the same. X value becomes negative. Jesus. Y value stays the same. Y value stays 1/2. X value negative root 3 over 2. Let's make that negative more convincing. And that, you know what, that's just illegible. There we go. That's a little better. Yeah, that feel pretty okay? And you know what, let's also think about tangent, but let's not think about it algebraically right now. Tangent is the slope. Those two orange lines I just drew, how do their slopes seem to compare? Let's see, their rises and then runs are both like equal, right? But negative of each other. So tangent changes by a negative sign. Negative root 3, negative 1, negative root 3 over 3. All right. And in fact, in general, tangent of pi minus theta seems to be the same thing as negative tangent theta. Nice. That seemed pretty good. I guess there's one quadrant left in the unit circle. Let's try to figure that out. So this angle, negative 5 pi over 6. Well, see, there's a negative there. Cosine doesn't care about a negative inside of the parentheses. Sine pulls it out front. Do I already have 5 pi over 6 somewhere on the unit circle? Yeah, we just figured it out, right? So these entries should be the same as those entries, but the y values become negative. So negative root 3 over 2, negative 1/2, negative root 2 over 2, negative root 2 over 2, negative 1/2, negative root 3 over 2. Each of these are negatives of those. Cool. Folks feel pretty all right? How will the tangents change? They'll become positive instead of negative now? Which makes sense. Negative divided by a negative will be positive. Cool. So now you have all of the entries in the unit circle filled in. There are two more moves that I want to talk about. One of them is pi over 2 minus, and the other one is pi over 2 plus. And we could think about pi over 2 minus using the unit circle again and doing some symmetries. Instead, here's a diagram we've seen before. There's an angle theta. Here's some unknown angle. This is a right triangle. So I guess that's an angle of pi over 2 right there. Pi over 2 is a right angle. Could you figure out that missing question mark angle? I think so. What do angles in a triangle have to add up to? Yeah.
It would be half of theta.
Half of theta. Why half of theta?
Because isn't that a 30, 60, 90 triangle?
This isn't drawn to scale.
Okay.
That other angle could be anything you want, but on paper I can't build something where you can change the angle. So so it's not that.
Okay.
Right, this angle could be 10 degrees, it could be 45, it could be 76, whatever.
Well, it has to be theta plus 90 minus 180.
Cool, let's write down the equation that you used to get that. Angles in a triangle add up to 180. Theta plus pi over 2 plus question mark equals 180 degrees, except I've been walking in radians all day. So let's use radians. Pi radians. Right, otherwise you'd have to convert that to degrees also, and I just don't want to. So I guess I need to subtract all that stuff to the other side, except for the question mark. Question mark equals pi minus pi over 2 minus theta. Don't know what theta is, so I can't simplify it, but I can simplify that. So this missing angle is pi over 2 minus theta, which is why this triangle is relevant to think about pi over 2 minus theta. So, using this triangle, this is a right triangle, so I can use SOHCAHTOA. There's y, there's x, and you know what, let's label the hypotenuse as h. So, SOHCAHTOA, what's the cosine of theta using this triangle? SOHCAHTOA, cosine is adjacent over hypotenuse. What's the adjacent side length? To theta? So you're answering something relevant. If I want pi over 2 minus theta, then it'll be y over h instead of x over h. Could we do the same for sine? So if I want pi over 2 minus theta, I can do that. Sine of theta, there's theta. Opposite is y. Adjacent is h. Ooh, two things are the same. So the cosine of pi over 2 minus theta is the same as the sine of theta. What about the sine of pi over 2 minus theta? What ratio is that equal to? There's pi over 2 minus theta. Opposite is x divided by hypotenuse is still the same. Ooh, so I already have a name for that in terms of a trig function though, right? X over h is also equal to that angle. So I also see sine of pi over 2 minus theta equal to cosine theta. Now let's just put that last entry in this table, and then I'm pretty close to out of time. When you do pi over 2 minus, cosine becomes sine, sine becomes cosine, and there's not a symmetry that I use to get this. These are just opposite angles in a right triangle. And you know what? Let's close by just looking at a Desmos Interactive, see if it looks like that means the x and y values just need to swap. So let's pull up this Desmos Interactive with the unit circle and see if that's what happens. Alright, so taking a look at that, does it look like between the blue line and the red line, the x and y values are just interchanged? Looks like. They're reflected over the line y equals x. Neato. So, with that being said, we will meet again tomorrow. We'll fill in a little bit of what's left here. Take a look at what you can in the web walk. On your way out, if you didn't grab a copy of the sample for this coming midterm and you want a physical copy of the sample, then feel free to grab one. If you're happy with the electronic copy, then you don't need to take it.